We finally reached the end of our hypothesis testing procedure, and now we're going to go through the last few steps where we get to determine whether or not our result is significant enough to lend support to our alternative hypothesis. So to pick up where we left off, we started out the hypothesis testing procedure by stating null and alternative hypotheses. And along with that, we chose a confidence level and therefore an associated alpha value. And we decided whether we wanted to run a one-tailed test or a two-tailed test. And then in the last lecture, we learned how to calculate our test statistic. And we calculated this t-score because we always need to use a t-test when population standard deviation is unknown. Once we have our t-score or our t-test statistic in hand, we need to determine whether or not that score is significant enough to reject the null hypothesis. And we can determine that significance in one of two ways. We can do it by looking at the p-value, or we can do it by looking at the critical value. So we have two options here. If we use this p-value method, then we're going to follow just 3 steps here. So we're going to locate the t-score, our t-test statistic, in the t-table. And we'll do that by navigating to the appropriate row based on degrees of freedom, and then scanning across the row until we locate the t-score. Once we find the cell in the t-table where we're positioning ourselves, we'll look at the corresponding upper tail probability at the top of the t-table. And then based on the kind of test that we're running, we'll use that upper tail probability to determine p-value. And then we'll compare that p-value to the alpha value that we set out at the beginning when we picked a confidence level. And we'll go through these steps in detail with an example. Otherwise, if we use the critical value approach, then we're following just 2 steps. This time we use our degrees of freedom, remember based on sample size, and the confidence level to locate a critical value in the body of the t-table. And then we compare that critical value to the absolute value of the t-score or the t-test statistic that we calculated earlier. And then based on what we find, here are the important conclusions that we can make. If we use the p-value approach, then if p is less than or equal to alpha, we reject the null hypothesis and therefore lend support to the alternative hypothesis. If we use the critical value approach, if the absolute value of t, our t-score we calculated when we found the test statistic, if the absolute value of t is greater than the critical value that we get from the body of the t-table, then we reject the null hypothesis and therefore lend support to the alternative hypothesis. So that's a lot to take in. It'll be much easier to understand if we go through an example. So let's pull up here a t-table, and I've consolidated this table so we're just showing the rows for 18, 19, and 20 degrees of freedom instead of looking at the entire t-table, because we're going to go through an example here where we choose a confidence level of 95%, therefore an alpha value of 5% or 0.05, and we'll run a two-tailed test. And more specifically, we're going to say that we use a 20-person sample, or that our sample size is 20. So because our sample size is 20, remember then that degrees of freedom is always the sample size minus 1. In our case, that's 20 minus 1, or 19. So that's why we're just looking at this section of the t-table, because we're going to be looking at this second row here where we have 19 degrees of freedom. So to go back to the beginning here, what we're saying is that we are running a two-tailed test. We've decided to run a two-tailed test because we're not sure about the directionality of our hypothesis statements, which means by definition that the null hypothesis has to be that the population mean is equal to our hypothesized value, and we're going to say that the hypothesized value here is 14. That means that our alternative hypothesis is that the population mean is not equal to 14. In the last few lectures, we've been using this hypothesized value where we say that we're running the shipping department in a warehouse and we're investigating whether mean order processing time is 14 hours. Let's say that the assumption is that mean order processing time is 14 hours. We're going to run a two-tailed test to investigate our alternative hypothesis here that mean order processing time is not 14 hours. So we have these hypothesis statements. We can see from the hypothesis statements that we're running a two-tailed test because of the fact that we have the equal sign and the not equal to sign. Otherwise, if the alternative hypothesis was mu greater than 14 or mu less than 14, then that would indicate a directional test and therefore a one-tailed test. but we have these hypothesis statements. We're running a two-tailed test. We've chosen a confidence level of 95%. That means that the alpha value is 100% minus 95%, or 5%. We can also call that alpha value 0.05 if we convert to decimal form there. And we're saying that we have taken a sample of 20 orders in our warehouse. We computed a sample mean of 14.45 hours with a sample standard deviation of 1 hour. And so our next step then is to calculate the t-test statistic. And so we have our formula. We looked at this in the last lecture. If we plug in everything that we have here, the sample mean we said was 14.45 hours. We subtract the hypothesized value, 14 hours, and then we divide that by sample standard deviation, which is 1 hour, divided by the square root of the sample size. And in our case, the sample size here is 20 orders. Now, if we use a calculator to find this value, we get a t-test statistic of approximately 2.012 when we round to 3 decimal places. So at this point, we have taken care of all 3 of these steps here and the whole first part of our hypothesis testing procedure. And now we need to either use the p-value approach or the critical value approach to make a conclusion about whether or not this t-score is significant enough to allow us to reject the null hypothesis. So let's look at the p-value approach. If we use this approach, here's what we do. Once we have our test statistic, we locate this test statistic in our t-table, and we do that based on degrees of freedom. So in this case, with a sample size of 20, degrees of freedom is 20 minus 1, or 19. So we go to the row where we find 19 degrees of freedom, and then we start moving our way across the row looking for 2.012. Now, keep in mind that it's very, very unlikely that we'll find exactly this value for the t-score that we calculated. Almost certainly, we'll find a t-value here that lies in between 2 of the values in the table. So looking across this 19 degrees of freedom row, we see that this score right here lies in between these 2 values. It's in between 1.729 and 2.093. So since we're in between these 2 values, and our next step is to locate the corresponding upper tail probability, we want to look at the upper tail probability associated with both of these values, the value to the left and right of the approximate location of our t-score. So if we go up to the top of our t-table, we can see the upper tail probabilities associated with those 2 values here, 0.05 and 0.025. Now, usually what we'll do at this point, because we know that our t-score is somewhere in between these 2 values, we'll pick some value in between these 2 upper tail probability values, some value between 0.05 and 0.025. So let's just say, for the sake of argument, that we split the difference equally. In other words, we take the halfway point between 0.05 and 0.025. Well, the value exactly halfway between these 2 is 0.0375. Now, once we found this value here, if we are running a two-tailed test, which is what we're doing here, we need to multiply this value by 2. So we would take 2 times 0.0375, and we get 0.075. And this then is the p-value. P-value is equal to 0.075. Now, here's the reason that we multiply that value by 2. When you hear p-value, think probability value. The value of p is essentially giving us the probability of rejecting the null hypothesis. Or another way to put that would be the probability of falling within the region of rejection. And another way to put that would be that it represents the amount of area under the distribution that makes up the region of rejection. And that's normally what we imagine alpha to be, which means that if we get a p-value that is smaller than the alpha value, it means that we're going to fall within the region of rejection and therefore that we can reject the null hypothesis. But if we get a p-value that is larger than the alpha value, it means we're falling outside the region of rejection and therefore that we won't be able to reject the null hypothesis, we'll fail to reject it, which is why we can compare the p-value directly to the alpha value. We want to look at them in direct comparison, and that's why we double this value that we found here when we're running a two-tailed test, because from the t-table, we just get an upper tail probability value, And so this estimate here is an estimate of the amount of area we'd find in the region of rejection in the upper tail. But if we're running a two-tailed test, we expect this same amount of area in the lower tail. And so to find P for a two-tailed test, we have to double this value to capture the full region of rejection from both tails. So for a two-tailed test, we double this value that we find, and then we compare that doubled value directly to alpha. In this case, alpha is 0.05 and P is 0.075. So within this particular set of circumstances, P is greater than alpha, which means that we'll fail to reject the null. We can't reject the null hypothesis. If instead of using the p-value approach, we use the critical value approach, then our first step is to locate the critical value in our t-table. What that means is that we look up degrees of freedom and our confidence level. So here, for this example, we know we're at 19 degrees of freedom at a confidence level of 95%. So we come to 19 degrees of freedom and move across until we see that confidence level of 95%. And that puts us here at this critical value. We call this the critical value when we find the intersection of those two things, 2.093. So 2.093 is our critical value. And we want to compare the absolute value of the t-score that we calculated. Remember that absolute value just means taking the positive version of whatever value we have. So even if here we had calculated t is negative 2.012, the absolute value of negative 2.012 is just positive 2.012. The absolute value of a positive number is itself. So all this means here to take the absolute value of t is if we come up with a negative value for t, taking the absolute value just removes that negative sign and turns the negative number into a positive number. Positive numbers stay the same. So here we have a positive number. Taking the absolute value means it stays the same. So we're comparing positive 2.012 to the critical value of 2.093. What we're showing here is that the absolute value of t is the absolute value of 2.012 compared to the critical value of 2.093. Well, that is less than 2.093. And because our t-score is less than our critical value, we fail to reject, we can't reject the null hypothesis. We need our t-score, the absolute value of our t-score, to be greater than the critical value in order to reject the null hypothesis. So then in this scenario, the conclusion of our hypothesis test is to say that based on the sample values we calculated, the sample mean and sample standard deviation, at a sample size of 20 orders, and to be 95% confident running a two-tailed test, we fail to reject the null hypothesis. We can't reject the null, which means that we can't lend support to our alternative hypothesis. There's no evidence here, or there's not enough evidence in this result to support the idea that mean order processing time is something other than 14 hours. And that would then be the conclusion of this hypothesis test. But let's look at what happens if we run a one-tailed test instead of a two-tailed test. So we keep the same confidence level and therefore alpha value. We want to be 95% confident. But instead, this time, we're running a one-tailed test, which means therefore that we have to change our hypothesis statements. We'll say that we're going to hypothesize that mean order processing time is greater than 14 hours. Therefore, the null hypothesis would need to say that mean order processing time is not greater than, meaning less than or equal to 14 hours. So we change our hypothesis statements, but we still took a 20 order sample. We found a sample mean of 14.45 hours, a sample standard deviation of 1 hour, and of course this is still our hypothesized value, which means we're going to compute the same t-score, the same t-test statistic of 2.012. Now let's go back to our p-value approach. But first, when we look here at our t-table, we need to be careful because this t-table is really set up for two-tailed tests. If you can see here, the confidence level across the bottom, let's take this 90% confidence level here. That means the alpha value would be 10% for this confidence level, which means that if we're running a two-tailed test, we'll have 5% of the alpha value. That 10% alpha value will be divided between 5% in the lower tail and 5% in the upper tail. And you see here, the upper tail probability that corresponds to 90% is a 5% upper tail probability, which means that this t-table by design is representing a two-tailed test, because this upper tail probability, if we match it up to the confidence level, by definition is showing that upper tail probability for a two-tailed test. So we need to be aware of that this row here, this confidence level row that's given to us by default, is for a two-tailed test. If we're running a one-tailed test, notice that these confidence levels shift over one column to the left, while upper tail probability stays the same. So for that same 90% confidence level that was here, if we have a two-tailed test, we know that that 10% alpha value gets divided into 5% in the lower tail and 5% in the upper tail, which we see right there. But for a one-tailed test, that means the entire 10% alpha value is going to be put into one tail alone. So we shift these confidence levels over one column to the left so that this confidence level of 90% corresponds to the upper tail probability of 10%, because the entire 10% alpha value that's associated with this 90% confidence level is pushed into one tail. So we need to see 90% confidence with 10% alpha in a one-tailed test versus 90% confidence with 5% alpha in a two-tailed test, which means then that if we're going to use this p-value approach and follow these steps again, if we again locate our t-score in the t-table, so we calculated a t-score of 2.012, and based on the degrees of freedom of 19, we locate that spot in this row, and again, just like before, we find this spot right here in between 1.729 and 2.093. We locate the corresponding upper tail probability, so we come up here to the top. Because we're in between these two values, we're in between these two upper tail probability values, 0.05 and 0.025. So if we then pick a value that's exactly halfway between those two, we pick 0.0375, that's exactly halfway between 0.05 and 0.025. But because we're only running a one-tailed test, we do not double this value like we did before when we were running a two-tailed test. Now we keep the p-value as just 0.0375. So this time we get p equals 0.0375. We compare that to our alpha value of 5% or 0.05. And we see here, in this case, that p is less than alpha. And based on that finding, we reject the null hypothesis. So this is here the two-tailed scenario, and this is the one-tailed scenario. So in the one-tailed scenario, based on the p-value approach, we're able to reject the null. What about using the critical value approach with a one-tailed test? Well, here we again locate the critical value in the t-table based on degrees of freedom and confidence level. So 4 degrees of freedom, 19, and a confidence level of 95% using our one-tailed test row for confidence level. So 19 degrees of freedom over to 95% confidence, and we arrive here at 1.729. So our critical value this time, remember last time it was 2.093, now it is 1.729. And let's put this one here in white to indicate that it was part of our two-tailed test. So for the one-tailed test, we get 1.729 as the critical value. We need to compare now the absolute value of 2.012, so absolute value of 2.012, and we need to compare that to the critical value of 1.729. Well, in this case, 2.012 is greater than 1.729, and because we get this greater than value, we can again reject the null hypothesis, which means that if we run this as a one-tailed test, then we are successful at rejecting the null and therefore successful at lending support to the alternative hypothesis. So in this case, we would say that we've found evidence for the idea that mean order processing time is longer than 14 hours. The conclusion of this particular hypothesis test with this particular sample that we found supports that result, supports that conclusion that mean order processing time is more than 14 hours. So under the exact same set of circumstances, we failed to reject the null for the two-tailed test and succeeded at rejecting the null for a one-tailed test. Remember all the way back at the beginning when we talked about hypothesis statements and one and two-tailed tests, that we said that the two-tailed test was more conservative and that we should only use a one-tailed test when we had some kind of data, some kind of evidence to give us a reasonable belief about the directionality of the test. And that's because with the entire region of rejection shifted into one tail of the distribution, it makes it easier for us to clear that bar and move out of the region of acceptance and into the region of rejection, and we are more likely to reject the null with a one-tailed test. The two-tailed test is more conservative, and if we don't have a good reason, some strong suspicion to expect the directionality of the test, we should use the two-tailed test since it is more conservative and harder for us to reject the null hypothesis. It's usually better to run a two-tailed test and fail to reject the null or find no significance than it is to run a one-tailed test and reject the null when we actually shouldn't, especially if the stakes are high. Like we talked about before, especially if our hypothesis testing procedure relates to something like health and safety, and we need to be really, really sure of our results. We want to bump up this confidence level as high as we can and make sure that we don't make a wrong decision here. Especially in a scenario like that one, it's better to be more conservative and run this two-tailed test unless we really, really have a good reason to state a specific direction in our hypothesis statements and run a one-tailed test. But either way, that is the conclusion of the hypothesis testing procedure. This is the process we'll follow over and over and over again in inferential statistics. And it always ends this way, where we calculate our test statistic, and then we use either the p-value approach or the critical value approach to determine whether or not that statistic is significant enough to allow us to reject the null hypothesis and therefore lend support to our alternative hypothesis.